I was so excited by the progress that I made before my last video that it wasn't until I was at the video editing stage that I realized that the analog video quality was not quite what I was expecting. So I got up close and personal looking at it on my monitor and then on my test equipment, and I started to worry. I was worrying about parasitic capacitances and impedance matching and power supply rejection ratios and all of those sort of things. And I thought this is going to be a really long journey to fix. Turned out that 99% of the problems were configuration issues, software issues in the way I'd set up the registers for the digital to analog converters. So I wanted to use this video to talk about how I fixed sort of 99% of those issues and give you an update on the fact that not only do we have the DACs working, the digital to analog converters, but we also have the analog to digital converters working. And in fact, the video that you're looking at right now is in the analog domain. And I think it looks pretty good. Still a little bit more I'd like to fix, but definitely imperceptible on 8-bit compressed YouTube quality land. So the issues were with the DACs. So what's special about these DACs? Well, if you look at the data sheet, the very first word on the data sheet is, or very first phrase is all format video digital to analog converters. So it begs the question, why am I using video digital to analog converters versus just regular digital to analog converters? What's the difference? It comes down to three things why you'd use a video-specific DAC versus just a generic DAC. The first is that you really want as much dynamic range to be dedicated to the video signal. If you look, and I'll put it up on the screen now, at an analog video signal, most of the video signal is in this range here, whereas you have the sync pulses going negative below the video range. Now, if you had a 10-bit DAC, so that means 10 bits per channel or 30 bits per pixel, because there's 3 channels of information, you'd be giving up an entire bit per channel just to represent the sync pulse. And the sync pulse is common in all video formats, in all analog video formats. So if you use a video-specific digital to analog converter, it'll contain circuitry in there that will know when the sync pulse is supposed to be, and it'll save the 10 bits, the 1024 values just for the video, and it'll trigger the sync pulse generation separately. So you're not giving up a couple of bits of resolution just for the sync pulses. The second reason why you use a video-specific DAC is cost. You can buy off-the-shelf generic DACs, and while this DAC can work as a generic digital to analog converter, video DACs are generally more common in some ways, particularly at this bit depth and sample rate. And it's cheaper to get a 3-in-1 package versus 3 specific DACs that have the same performance as the DACs that are inside a video DAC. And the last reason is functionality. And that's not particularly relevant to my use case because the ASIC that I'm using provides all of this functionality. But a lot of DACs and ADCs that are designed specifically for the video domain include arbitrary color space transformations. So you can input RGB, output YUV, you can adjust brightnesses and all of those things. And so what was the problem that I was having? Well, I was having a lot of problems, and they're all software problems. They're all me problems. Because this is an all format digital to analog converter, you need to be very careful in how you're setting up the registers to generate the sync pulses. The DAC itself has its own clocking circuit that generates the sync pulses, and it operates that clock somewhat independently of the data clock that you're sending the parallel bits of data in. And I managed to get it set up so it was working in the sense that I could see a picture on my screen and it looked good, but it was a little bit blurry, and you may have noticed that there were some black dots coming out. Somehow I was confusing double data rate with the double clocking rate of the PLL inside the DAC, and it was a bunch of stuff. I was just so excited to get it working good enough that I shared the video. But after spending some time going deep, I realized that it needed to be configured a lot better. And I think it is a lot better now. The other big thing that I've done is I've got the ADCs working. So that is the analog to digital converter path. In the last video, I took the analog video and put them through a commercial Blackmagic ADC, and that worked okay. But the ADC that I have working now is significantly better. Firstly, it's 444, which means that there's no chroma subsampling. In typical analog video, you're used to the idea of giving up bandwidth for color information. Color's not as important as general brightness. typically, because analog video is typically the very end of a workflow chain. We've done all of your color timing, your color correction, you've done your tone mapping and all of those sort of things. And so if you lose a bit of resolution in the color space, it's kind of okay. But I'm designing a tool that's designed to be sort of in the center of a video processing workflow where you really want that raw 444, no chroma subsampling. The other thing that this DAC does is it's 12 bits per pixel, or 12 bits per channel, which means 36 bits per pixel. That is an extraordinary amount of dynamic range. Your typical, the video that you're watching now on YouTube has been uploaded and transcoded to 8 bits per channel or 24 bits per pixel. That's perfectly fine for sort of end of the chain video signals. But the camera that I'm shooting on right now is a pretty good camera, and it outputs 12-bit raw video. The reason why you want to have more dynamic range in your sources rather than in your output is that you may want to, after the fact, adjust brightness levels or bring up some mid-shadow highlights or words like that. And when I'm working with the signals that I'm planning to work with, or I want to enable you to work with as well, is you'll be taking video from the digital domain, sending it out as analog, putting it through analog circuitry, where you might get saturation of the highlights, or you might get a lot of detail sort of lost in the shadows, and you may want to bring those details up and make them more visible in the finished product. And so having a really high dynamic range, or a 12-bit per pixel, 36-bit per pixel, 12-bit per channel ADC enables you to do that. But that means I've got to be super careful, and this is what I come down to the last 1%. I've got to be super careful with the voltages and the noise on the board. So the DACs are outputting 30 bits per pixel, 10 bits per channel. So you're taking roughly a volt of data and you're dividing it by 1024. So you've got roughly a little under a millivolt. Video standard voltages, whatever. Roughly under a millivolt of your noise floor. You want to be a little bit under that. When you've got a 12-bit analog to digital converter, you're multiplying that noise floor, or you're dividing that noise floor by a factor of 4. So you're really down into the microvolt level. And that's sort of the level that I'm at right now. And I want to get it better so that we're not losing any of the last significant bits. Or it's really the last significant bit that I'm worrying about now on the ADC side. Now, of course, none of this matters at all for the video that you're seeing right now. It's completely lost the moment you convert it to 8-bit video. But to enable cool effects and deliver the quality that these devices can promise, I really want to keep the noise floor good. So the title of this video was 4K component video. Now, the great thing about using this all-purpose digital to analog converter is that it really is all format. I can output 4K video, 10 bits per channel, 30 bits per pixel in the component domain. And on the oscilloscope, it looks great. Why aren't I showing it to you now? Well, I'm not showing it to you now as video because I don't have an ADC that's capable of receiving that video. Now, the ADC that's on the board, technically in terms of bit depth and sample rate, is able to, in the analog domain, process that video. But this chip that I'm using is, again, it's a video ADC. It's not even a video ADC, it's a video HDMI receiver. It's a single chip that's put out by Analog Devices that's designed to go in the back of TVs or high-end broadcast equipment that takes high definition video and transceives it from HDMI to parallel bits of information. It happens to have an ADC in it. I'm not using any of the other stuff. I'm just using the ADC. But because it's designed to go into existing video equipment, it only supports existing video formats. So it doesn't really know what to do with 4K analog video. Now, 4K analog video is interesting. It really puts you in the electronics world into the RF engineering domain. You've got really fast transitions that you have to deal with, particularly with high contrast edges. While I technically could do it if I switched out the ADCs, it comes back to that question of cost. The chip that I'm using right now, I can't remember off the top of my head, it's roughly a $20 to $30 analog to digital converter. Again, as I said, it's more of an HDMI receiver than analog to digital converter, but I can use it. Oh, it's got an analog to digital converter in there. If I wanted to get an appropriately spec'd single channel analog to digital converter that can do 4K video, we're looking at like 30, $40 per channel, and you need 3 of those. And while it would be nice to slap a 4K logo on the front of this box, it's not worth the additional BOM cost. Not only is it, another $100, $200 of BOM cost that you're putting into the device, there's a lot of programming, a lot of circuit board space you'd need to take up to get this thing to work. So it's not worth it in the end. But it's cool to know that at least on the transmission side, I'm able to transmit 4K analog video. Might be interesting to someone. Anyway, quick update. I'm about to head overseas, so I thought I'd just give a quick update on where I'm at and share with you the 99% improved video signal. Catch you next time. Bye. In fact, the video that you're looking at right now is in the analog domain, and I think it looks pretty good. Still a little bit more I'd like to fix, but definitely imperceptible on 8-bit compressed YouTube quality land.